Polynomials. Our objective is to identify, evaluate, add, and subtract polynomials, as well as classify and graph polynomials. Who uses this? Doctors can use polynomials to model blood flow. Let's start with some vocabulary. A monomial is a number or product of numbers and variables with whole number exponents. A polynomial is a monomial or sum or difference of monomials. So, for example, we have 3x to the fourth. That would be an example of a monomial. Then you have 2z to the 12th plus 9z to the third. We are adding two monomials. We could have 1/2 a to the 7th, 0.15 x to the 101, 3t squared minus t to the third. These are all examples of polynomials. These next ones are not polynomials, like 3 to the x. You have your variable as an exponent. And you have the absolute value of 2b to the third minus 6b. Can't have absolute value. Then you have 8 divided by 5y squared. Your variable is in the denominator. You're not adding or subtracting. You have 1/2 the square root of x. You have m to the 0.75 minus m. So you're not raising your power to a whole number. So those would be examples that are not polynomials. Now let's look at the degree of a monomial. It is the sum of the exponents of the variables. Remember, a monomial is just one term. When it's the one term, you add the exponents of the variables. The degree of a polynomial is given by the term with the greatest degree. So when you're trying to find the degree of a polynomial, you need to figure out what each of the monomials are first. And then the leading coefficient is the coefficient of the first term when you've written it in standard form. So let's start by identifying the degree of a monomial. So we need to add our powers. We have x to the fourth. Well, there's only one number there, and it would just be 4. In example B, notice how there are no variables. You can technically write x to the 0 if it helps you determine the degree. So a constant is always going to have the degree of 0. Now let's look at C. We have 4a to the second b. When b is by itself, or any variable is by itself, you can raise it to the first power. Just because it doesn't have a number next to it doesn't mean it's 0. 0 would mean it doesn't exist. So we have a to the second, b to the first. We add those exponents together, giving us a degree of 3. And now we have x to the third, y to the fourth, z. So now we add our exponents. So 3, 4, and 1 provide 8. Standard form. The leading coefficient is the number in the lead, if you will, and it's the number in front of the variable. A leading coefficient is a coefficient, so it's just the constant in front of your variable. Your degree of each of your polynomial is going to be the largest degree. So notice how the degree of each term is listed below. So we have 5x to the third, so the degree of that term is 3. 8x squared, the degree of that term is 2. 3x, the degree is 1, and minus 17, the degree is 0. So when you put it in standard form, you go from largest degree to smallest degree, and then the degree of the polynomial is simply the one that is the largest. You can use this to classify polynomials by degree. So if you have something that is a 0 degree, it is a constant. So that would be like -9, 7, 3. when it's just a number. There are no variables. If you have something that is 1 degree, meaning you have an x kind of all by its lonesome, you could have like 3x minus 4, but x is to its own, just a power of 1, and that's the highest degree. That would make it linear. To have something that's quadratic, the largest degree is going to be 2. So the term with the largest degree in this example is 2. Yes, you have a 3x, but you only need to classify it by the one that's the largest degree. A cubic, the largest degree would be 3. A quartic, your largest degree is going to be 4. And quintic, your largest degree is going to be 5. Let's use those classifications to help us. So we're going to rewrite each polynomial in standard form, then identify the leading coefficient, degree, and number of terms, and finish it off by naming the polynomial. Alright, so let's write it in standard form. We need the largest power, so we have 4x to the third, and we have a positive 2x, and then a minus 1. So our leading coefficient is 4. The degree is going to be 3, since that's our largest. And the number of terms is going to be 1, 2, 3. So now we get to name it. So since our degree is 3, we revert back. A degree of 3 makes it cubic. So we have a cubic. And we have 3 terms, and, well, one term is a monomial, and from a previous section you should know that 2 terms is a binomial, and 3 terms would be a trinomial. So it's a cubic trinomial. Take a moment and pause the video and try to do B on your own. When you return to the video, the answer will be revealed. Alright, so as you see here, you have it in standard form. Your leading coefficient would be 1, your degree is 5, and the number of terms is 1, 2, 3, 4. Therefore, it is a quintic polynomial with 4 terms. So you'll use monomial, binomial, trinomial, and once you get to 4, 5, 6, and on, you're just going to say it's a polynomial with however many terms it was. Let's look at adding and subtracting polynomials. When you are trying to add or subtract polynomials, simply combine like terms. So we have 3x squared and a positive 14x to the third. Those can't go together. Well, there's no other powers that are 14x to the third, so that one's going to stand alone. And we have a 2, and we have a x squared. So we have 3x squared and x squared, giving us 4x squared. And that takes care of those. And now let's see if we have any x's. We've got x and minus x, so they kind of cancel each other out. And then we have a constant. We have 7 and 2, which provide 9. So by writing it in standard form to start with, that would be by taking your largest degree first and then finding your smallest degree as you keep going. Alright, so take a moment and pause the video and try B. Keep in mind you have a minus, so you need to distribute this minus all the way across, just like we kind of did with the addition. But when you add 14x to the third or add a positive 2, it doesn't change any of the signs. when you subtract a negative, you end up adding a positive. When you return to the video, the answer will be revealed below. So you end up with negative 4x squared minus 2x plus 6. Let's look at a medical application. Cardiac output is the amount of blood pumped through the heart. The output is measured by a technique called dye dilution. A doctor injects dye into a vein near the heart and measures the amount of dye in the arteries over time. The cardiac output of a particular patient can be approximated by the function f of t equals 0.0056 t to the third minus 0.22 t squared plus 2.33 t, where t represents time in seconds after the injection, and it is done between 0 and 23 seconds. The f of t represents the concentration of dye in milligrams per liter. So we're going to evaluate t for 0 and 3, so simply substitute 0 in and substitute 3 in. So f of 0 would be 0. F of 3 is going to be 5.1612. So now we're going to just verbally describe what the values of the functions from part A represent. So part A. So f of 0 represents the concentration of dye at 0 milligrams per liter in the artery at the start of the dye dilution process. So at time 0, there is 0 milligrams per liter. Alright, but how about after 3 seconds? There is going to be 5.1612 milligrams per liter in the artery. And that's your description. Let's look at graphing higher degree polynomials on a calculator. So for these next 4 pieces, you're going to want a calculator or graphing calculator handy. So we're going to graph each polynomial function on a calculator and then describe the graph and identify the number of real zeros. So we plug into our graph x to the third minus x, and we see this. So from left to right, the graph increases, decreases slightly, and then increases again. I like to call this my disco dance function. You kind of put a person in there, left arm, right arm, doing the disco dance. So it crosses the x-axis 3 times, so 1, 2, 3, so there appears to be 3 real zeros. Let's look at this next one. We have 3x to the third plus 2x plus 1. Your graph is going to look something similar to this. So it's been moved up 1, and it's been shifted over, and it's been stretched out by 3. So it still increases, and then increases less, and then increases again. So it still almost has this basic shape here. It crosses the x-axis once, however, instead of the 3 times like we have on the left. So there appears to be only 1 real zero. Let's look at these next 2. So we have x to the fourth minus 8x squared plus 1. So when you plug that into your calculator, you should end up with a graph that looks like this. So from left to right, the graph alternates, decreases, increases, decreases, and then increases. It crosses the x-axis 4 times. So, therefore, it's got 4 real zeros. 1, 2, 3, and 4. Alright, so now let's look at D. D gets a bit crazy here. We have x to the fourth plus x to the third minus x squared plus 2x minus 3. So that graph is going to look something like this. So from left to right, the graph decreases, then increases at a couple different rates here, and then increases all the way up. It's similar to this graph here, however, its shape kind of gets a little bit morphed, and therefore it only crosses the x-axis twice. So therefore only 2 real zeros. And that ends our video lesson.